Hello student, welcome to this numerical exercise part 2 in which we are taking the light and matter, that is a discipline specific course 9 of University of Delhi for physics honors students. Before we go to the numericals, let us quickly revise the important relations and the basic concepts that they will help us to solve the numericals. So we are starting with the very first topic, that is the interference of the two waves. Two waves, they are approaching a particular point, that is a point of interest P. The first wave and second wave, they have disturbance at point P given as A sine of omega t and B sine of omega t plus phi. There are two things which are very important to understand. The angular frequency must be same, and this phase difference between the two, phi, it must not be time dependent. It should be independent of time. If such condition is there, we can say that these two waves are coming from the coherent sources and will produce a sustainable interference pattern. When they meet at point P, they will superimpose each other and their resultant disturbance will be given by the vector sum of their individual disturbances, and as a result we get the amplitude, say A, that is our total amplitude, say sine of omega t plus delta, that is a resultant wave we have of the same frequency, where amplitude is given as under root of A square plus B square plus 2ab cos of phi. Now this phi will decide whether the amplitude is going to be maximum or minimum or anywhere in between. So this is a quite crucial part to decide the condition for maxima and minima. But before we go to these conditions, I would like to give you two more relations. One is that phase difference divided by 2 pi is equal to the path difference divided by lambda. This relation is important to convert the phase difference into the path difference, which I am representing as delta p. So you can talk in terms of the phase difference or in the path difference according to the requirement in a particular numerical. The second relation is the relation for intensity, which is supposed to be directly proportional to the square of the amplitude. For most of the simple purposes, the constant of proportionality, say that is k, is taken as 1. It may not be 1, but since we are most of the time comparing the maximum and minimum intensity, so when you divide the two, this k becomes irrelevant. So for ease, we are taking it as 1. It may not be, right? So now come to the condition for the maxima and minima, which is the major point when we solve the numericals on it. So it is the cos phi which is going to decide. So there are two possible conditions we have. One is a condition in which the amplitude or intensity is going to be maximum, and other condition is one in which amplitude or intensity is going to be minimum. This will happen when cos phi is equals to plus 1, and this will happen when cos phi is minus 1. So the amplitude maximum is going to be A plus B, and amplitude minimum is going to be A minus B. I used a modulus sign here because it is possible A may be more or B may be more, right? So we are avoiding the negative of this difference. That's the reason. For cos phi to be plus 1, the condition is that this must be plus minus of 2n pi, where n is an integer. It can be 0, 1, 2 and so on and so on. Similarly, for the minimum condition, this is going to be plus minus 2n plus 1 pi. That means odd multiple of pi. Or in terms of the path difference, you can say this is plus minus n lambda, and this is going to be plus minus 2n minus 1 lambda by 2. So they remain the basic conditions for the maxima and minima, whatever the case may be. When we talk about the interference of the two waves, so these conditions are not going to change. However, the formulas, various formulas can be modified according to certain special condition which we'll see while dealing with the other topic. But these are the basic condition with which we'll keep the interference pattern for the maxima and minima condition. So students, let's start with the first numerical. In the first numerical, the information given to us are wavelength is 500 nanometer, the slit spacing is 0.2 millimeter, the distance between the slit and screen is 1.5 meter, and a very thin transparent sheet of 0.005 mm is inserted on one side and has a refractive index of 1.6. The first thing they want from us to know that what is the optical path difference introduced when this slit is put into the picture. Let's understand, there is a relation between optical path and the geometrical path like this. Optical path is mu times the geometrical path. When you insert a transparent sheet of thickness T, in fact this now is making the light to travel an optical path of refractive index times its thickness, whereas initially the light was traveling only the geometrical path T. So the path difference introduced in this case now is equals to mu T minus T, or you can say is equals to mu minus 1 of T. So this mu is given to you 1.6 minus 1, and the thickness is 5 into 10 to the power minus 6 of meter is millimeter, and you have say up to 3 decimal places, so this much is there. So now if you calculate it out, this comes out to be 3 into 10 to the power minus 6 of meter. So this is the optical path which is being changed by putting the transparent sheet into the picture. The next thing he is asking, that is how much is the shift, and for the shift we have discussed this point, the delta x is going to be, or delta y, you may take any of the sign for it, that is equals to mu minus 1 of t multiplied by d, capital D divided by small d. This is the shift of the central maxima which has been done, and that is equals to 1.6 minus 1. The thickness is t into 10 to the power minus 6. D is 1.5 meter, and small d given is 2 into 10 to the power minus 4 of meter. 0.2 I have just taken it as 0.4. Now if you simplify it and calculate this, this will come out to be 2.35 into 10 to the power minus 2 of meter. That means our central maxima will shift towards the side of the slit where we have kept this transparent sheet by a distance which is equals to 2.35 10 to the power minus 2 of meter. So let's take the second numerical. In this numerical, it is given to us that the two interfering waves, they have their intensity ratio as alpha. And we are asked to show that I maximum minus I minimum divided by I maximum plus I minimum is 2 under root alpha 1 plus alpha. So let's start with the left hand side. As we know that intensity is directly proportional to amplitude square. So when you write this I1 by I2, I can write this as A1 square by A2 square is equals to alpha. So this makes A1 by A2 as under root alpha, or A1 is equals to under root alpha A2. Let me call this equation as equation number 1. So now we are taking I maximum minus I minimum divided by I maximum plus I minimum. And as we know that the intensity is directly proportional to amplitude square, and for maximum being a constructive interference, so crust comes on crust, making the net amplitude A1 plus A2, and for minimum it is A1 minus A2. And similarly in the denominator we have A1 plus A2 whole square plus A1 minus A2 whole square. This then will be equal to, if you simplify this, this will become A1 square plus A2 square plus twice A1 A2 minus A1 square minus A2 square, and minus will become plus twice A1 A2 divide by, similarly open this, A1 square plus A2 square plus twice A1 A2, and you have a plus sign here, so we'll write this as plus A1 square A2 square minus twice A1 A2. We can simplify it by removing these, and we write this as, this now becomes 4 A1 A2 divided by twice of A1 square plus A2 square. This 2 can be handled here. So this is A1 A2 divided by A1 square plus A2 square. Now in order to get the right hand side, since I know that A1 by A2 is equals to under root alpha, I am doing one thing. I am dividing and multiplying by A2 square. You divide numerator as well as denominator by A2 square. If I do that, then this will become twice A1 by A2. This A2 will be out with 1, and this is 1. I am writing 1, and then is A1 square divided by A2 square. So A1 by A2 already we have calculated as under root alpha, so replacing will give you twice under root alpha, and this is then 1 plus this A1 plus A2, and that is equals to alpha. So we have our answer as required in the numerical. So let's take the third numerical. In this numerical, it is given that a Fresnel biprism is kept in front of a source slit, and from the source slit at a distance of 30 centimeter, a lens is placed which is creating a sharp image at a distance of 1 meter from the source slit, which means that the distance between the lens and the screen is 70 centimeter, and we are required to find out the wavelength. It is given that the image of these virtual slits S1 and S2 as observed on the screen, which is say S1 dash and S2 dash, we get the inverted image as we know from the formula for linear magnification M, which is the height of the image to the height of the object and is equals to V by U. We get image distance minus d of I, the object separation which is d, is equals to plus 70 centimeter divide by, this is on the reverse side, so that's why it's minus 30 centimeter, which gives you d as, this is d, that's the distance required, is equals to di multiplied by 3 by 7. Since di given is equals to 7 mm, so 7 multiplied by 3 by 7, so this is equals to 3 mm. Once this is known to us, we can easily find out the wavelength from the expression for the fringe width, which is equals to capital D by small d. So wavelength from here is equals to beta d divided by capital D. So beta given to us is 0.2 mm and d, the distance d which we have worked out, this is equals to 3 into 10 to the power minus 3, and capital D in this case is 70 plus 30, that is 1 meter, and this comes out to be 0.6 into 10 to the power minus 6 of meter, or we can say 6000 angstrom. So this is the wavelength of the light for which is the answer for this particular numerical. So let's take the fourth numerical. In this numerical, it is given that a Fresnel biprism having the prism angle as 1 degree, made from a material of refractive index 1.55, is kept at a distance of 30 centimeter from the source slit. The distance between the source slit and the screen is 1 meter, and we are asked to find out what is the fringe width. The formula for the fringe width is lambda capital D by small d. Only small d is not given to us, but we have discussed in the initial section that if this type of situation is there, then the small d is going to be twice of a mu minus 1 of alpha, where a is this separation which is between the biprism and the source slit. But we have to keep this alpha in radian as we discussed in that case also. So this is 2 multiplied by 0.3, 30 centimeter is converted to meter, 1.55 minus 1, but 1 degree is equals to pi divided by 180 degree, that is in radian. And if you simplify this, this comes out to be 1 point small d is equals to 5.76 10 to the power minus 3 of meter. And when we use this d to find out the fringe width, that is equals to the wavelength, and wavelength given to us is 6 into 10 to the power minus 7 multiplied by distance capital D is 1 meter, small d already we have worked out, this is 5.76 into 10 to the power minus 3, and if you solve this, this comes out to be 1.04 10 to the power minus 4 of meter, or we can say beta is equals to 0.104 of millimeter. This is the answer for the numerical number 4. Now let's take the fifth numerical. In this numerical, it is given that there is a thin film illuminated by a monochromatic light at an angle of incidence equals to 60 degree. The refractive index of the film is 1.5 and the thickness we have to calculate for which, the minimum thickness for which it appears dark to us. Now we know that this light, when enters into the denser medium, it bends towards normal. So this angle is the angle of refraction. In the reflected mode, for minima condition, we have a relation 2 mu t cos of r is equals to L lambda. So the minimum value of n is equals to 1, because n equals to 0 means then no film is there. So n equals to 1 is the minimum possible value. So t minimum is equals to lambda divided by 2 mu cos of r. In the question they have given us angle of incidence and we have to find out the angle of refraction by using the Snell's law at this point. The Snell's law, in this medium the refractive index is 1. So sine of 60 degree must be equal to 1.5 sine of r. This is the best way of using the Snell's law. The same medium and the angle in the same medium, refractive index of this medium and the angle in the medium. So if you calculate, you will find that the angle of refraction comes out to be 35.24 degree. Once this is known to you, T minimum can be easily calculated. T minimum therefore is equals to the wavelength, and the wavelength is equals to 5.893 into 10 to the power minus 7 of meter. If you convert this angstrom to meter, you will get this. Then we have to multiplied by 1.5, that is the refractive index, and cos of 35 degree, 35.24 degree, and solving it will get this value as 0.24 micrometer, or you can write this as 2.4 into 10 to the power minus 7 of meter. So this is the T minimum for this. Film will appear to be dark to you because of destructive interference we get in the reflected mode. So let us take the sixth numerical. In this numerical, a wedge-shaped film is formed between the two glass plates. The horizontal distance maximum is 5 centimeter. Radiation of wavelength 6000 angstrom are coming almost normal to this film. And it is told that the first dark fringe comes at a distance of 0.5 mm from the edge where these two glass plates meet. And we are asked to find out the angle of the wedge. Now as we know that the condition for the minima for wedge-shaped film is 2 mu t cos of r equals to L lambda. Since first dark fringe comes at the distance as given, so we'll take n equals to 1. The refractive index of air is nearly 1, and since it is coming normal, so cos of r is also close to 1. That will make the equation as 2t equals to lambda, and this thickness t, where the first dark ring comes, can be written as angle is assumed to be small, so one can use the angle is equals to arc by radius, this concept, and this then is equals to x into theta. So from here the theta is equals to lambda divided by twice of x. Lambda is 6 into 10 to the power minus 7 meter, and twice of x, and x given is 0.5 mm. That means 5 into 10 to the power minus 4. And this makes the theta as, this is 10, 0.6, and from here minus 3. So this is 6 into 10 to the power minus 4 of radian. This is the answer for the first part of it. The second part requires that how many such fringes we are getting in the entire region of this film, that is L equals to 5 centimeter. So we have to find out what will be the maximum possible value of N. This we can calculate easily by taking the T maximum. Let's calculate first of all the T maximum. Since L given to us is 5 centimeter, so T max will be L multiplied by theta, and L given is 5 centimeter, 5 into 10 to the power minus 2, and theta already we have calculated. This is 6 into 10 to the power minus 4 radian. So this is 30 into 10 to the power minus 6 meter, or we can say 3 into 10 to the power minus 5 of meter. Once this is known to us, we can find out the N maximum by keeping the T maximum. So from here we write that 2T maximum is equal to 2T maximum is equals to maximum N maximum into wavelength. So N max will come out to be 2T max divided by wavelength, and T max already we have calculated. This is 3 into 10 to the power minus 5, and wavelength is 6 into 10 to the power minus 7. So we can easily calculate this. This comes out to be 100. So that means the maximum value of the fringes which are available in this region, that is equals to 100. So let's take the 7th question, and in this numerical it's been given to us that in a Newton ring setup in a reflected mode, the gap between the 5th ring and the 10th ring is 1.5 mm, and we are asked to find out the radius of curvature where the wavelength given is 600 nanometer. We know that for dark ring, the radius is given by this formula. So obviously, the radius of 10th ring minus radius of the 5th ring is 1.5 mm. That means 1.5 10 to the power minus 3. So let's put the expression for this. This is 10, the radius r. The wavelength is 6 into 10 to the power minus 7. Divide by 2 minus under root of 5 r 6 into 10 to the power minus 7, then divide by 2, and this is equals to 1.5 into 10 to the power minus 3. Once you write this expression, it becomes simple. Square both the sides and get the value of r. The value of r obtained by calculation is 8.72 meter. So let's take the 8th question now. And in this question it is given that the 10th dark ring in a Newton ring pattern has a diameter of 4.2 mm, where in the gap we have a transparent liquid whose refractive index is not known to us. The diameter of the nth dark ring is given as 4Rn lambda divided by mu. Mu is a refractive index. If it is air, mu is taken as 1, but if it is a liquid, we have to keep this mu there. Rest is quite simple, just we can simplify it. dn square is equals to 4R n lambda by mu. So the refractive index can be obtained as 4R n lambda divided by dn square. Now putting the value, this is 4, radius is 1 meter, the number of the ring is 10, wavelength is 5.893, 10 to the power minus 7, from angstrom to meter is already been converted, and this diameter is 4.2 into 10 to the power minus 3 whole square. If we solve this, we'll get the value of mu as 1.34. This is the answer for the question number 8. So let's take the 9th question. In this, an electron is accelerated from rest by a potential difference of 150 volt, and now this electron continuously are bombarding two slits at the separation of 1.2 micrometer, and a screen or detector is kept at a distance of 1.5 meter. Now we have to find out the distance between the central line and the first maxima. If we are not trying to find out the position of the electron in the slit, we are going to get the similar interference pattern, because in that case there is no collapse of the wave function occurs, and we are getting the similar interference pattern as normally we get with the waves. But we have to take the de Broglie wavelength of the electron. So treating it as a non-relativistic case, since energy of the electron is E into V, and that is half mv square, or can be written as p square by twice of m. So the linear momentum can be written as 2m ev under root. So the de Broglie wavelength is h by p, and we calculate for this electron the de Broglie wavelength. This is equals to 6.63 10 to the power minus 34 in the SI system, the value of h, and the momentum is given as twice the mass of the electron, 9.1 10 to the power minus 31, electronic charge as 1.6 into 10 to the power minus 19 coulomb, and the accelerating voltage is 150 volt. Calculating the wavelength, we get the wavelength near about 1.0 into 10 to the power minus 10 of meter, and the fringe width which is required, as we know, is equals to lambda d by d. So lambda in this case is de Broglie wavelength, 10 to the power minus 10. The distance is 1.5 meter, and small d given to us is 1.2 10 to the power minus 6 of meter. Everything is taken in the SI system. So this will come out to be 1.25 into 10 to the power minus 4 of meter. So this is answer for the question number 9. So let's take the 10th numerical. 10th numerical is for the interference by a single photon falling on a two slit. Now it's very interesting that if we are not making any attempt to find out from where this photon enters into which slit, it means there will be no collapse of the wave function. In that situation, this will be a normal interference experiment, and since we are required to find out the distance between the central position and the second maxima, that is equals to 2 beta, so y will be equals to twice lambda capital D by small d. 2, the wavelength given is 6 into 10 to the power minus 7, capital D is 2 meter, and small d given is 0.1 mm, that means 0.1 into 10 to the power minus 3 of meter. If we simplify this, we get the answer 24 mm for this distance. That is the answer for the question number 10. So with this, we close this discussion of the numerical exercise for interference. In the next section, we'll take the diffraction of light as well as matter. Thanks for watching.